Can you see my screen? I open some PowerPoint. If you can, let me know. Okay, you can see maybe. Can you hear me? Okay, so you can hear me. What about the screen? Can you see the PowerPoint file? Okay, very good. Thank you. Okay, so let me open the PowerPoint for the last lecture. And here, okay. Participants. And also the chats. Okay. Good. Okay. So last week we studied the basic programming. Of course, last session, lecture 2, the basic programming tools on PLC and what is that, and the relation between the PLC control system and the hardwire control system. I just want to review, very fast review, and then I ask you your question. I'm asking your question after that, if you have any question on this lecture, and then we will continue this session. So as a fast review, we studied that, okay, if you have a hard wire control system, for example, an electric motor with a start and stop, we want to convert that to a PLC base. In a PLC base, in fact, the logic is implemented by some software, but anyway, the PLC must communicate with the devices in the field. And so a PLC need also input and output modules that the devices in the equipment, in the machine, in the field, in the plant, connect to those inputs or outputs. And then considering the state of the inputs and the logic, the program, some command generates and is generated, and that generated command transmitted to the, or applied to the machine, to the motor, to the solenoid valves, and like that through the output modules. Okay, then we briefly studied what is the input-output cards. That are some terminals that the device directly will be connected to them. We will look at that in programming, but it is very important to notice that all the devices are connected to the PLC input and output modules individually, separately. There's not any connection between the devices outside of the PLC. Except that all of them, okay, yeah, they may need to be connected to the power supply. We don't assume that connection to the power supply, connecting to the power supply is a kind of connection between the devices. They need power, so all of them are connected to the power supply, or maybe they need to be grounded. Okay, many of them are connected, might be connected to the ground, but there's not any connection between them like this. Here, there are some connection between the devices, between the start, stop, push button, the auxiliary contact of this coil, even the coil and the start, all of them are wired to each other to implement the logic. But when we have a PLC program, there's not any connection. There's not any connection between the inputs or outputs or inputs and output devices, except that they might be connected to the power supply or a ground. So they connect, each of them connects to the inputs directly to the input devices, or if they are output devices, motor, switch, like pilot lights or like that, they are also individually connected, are connected to the output modules. But these terminals in the input and output modules, in fact, the PLC input-output card, let's say input card, read the voltage on this terminal, the voltage changes according to the state of the switch. So something that changes at the terminal of the input cards are the voltage, just signal, or maybe current. Of course, you have current base, but these are voltage base. But so the voltage change, or let's say electric signal change, the PLC card measure that electric signal, that voltage, or and then let's say assign the value of some memory in the PLC. So associated with each input and output card, there are some memory. Let me switch here. There are some memory part of the PLC memory. PLC, of course, PLC as a computer has lots of has a memory that divides between different parts, the program part, the data part, and like that. One part of that is for the inputs. So when the voltage here changes, the input card responsibility or the input card task is to read that, let's say measure that, and then according to that, change the state of these bits. For digital inputs, an input that has just two values, it has just two values, 0 and 24 volt, for example, 0 and 48 volt, or I don't know, 0 and 220 volt AC. For these type of inputs that we call them digital input, only we need one bit. A single bit is sufficient to represent the value of that. If the value is 0 volt, the voltage is 0 volt, the bit here is 0. If the voltage is 1 volt, the bit is 1. So single bit is sufficient. Of course, if the signal here changes in a range, something that we call analog signal, it's different. We will look at that and the analog signal later in one of the sessions, in two of the sessions in fact later. But just for the digital, very simple single input. And the PLC, in fact, when we address the input of the PLC, let's say the CPU, does not go or check the value of the voltage at the input terminal. It checks the state of the bit on the memory, something it's called input image memory or input. Similarly for the output. So the PLC program changes the state of some memory. This memory is associated with some output terminal or some output card. If the memory is 1, for example, if it is a digital, if the memory value, that single bit memory value is 1, the output module applies 24 volts on the output of its terminal, or apply 220 volt AC. If it is 0, it applies 0 volt. And that 0 volt or 24 volt do the job in the field. It is connected to the light turns on, it is connected to the coil of the contactor, so the contactor energizes and like that. This is how the PLC communicate with the outside devices in the field. Okay, so yeah, studying input output, and we studied also the standard format for the Siemens PLCs, I for the input, Q for the output, and memory, let's say memory address, the address of the memory byte, byte number 1 or byte number 4, that these bytes are associated with some slots, input-output modules or input-output slots. So they also may call, sometimes we call them slot number instead of byte number. But both is correct. There are some slightly different between them. Later I will mention that. But let's just call them byte memory or slot memory. We can use both of them. And then the bit memory, if it is digital. If it is digital, okay, just one bit of that, the bit memory. So this is the standard of the input-output addressing. Then we studied logic functions, how to implement logic functions. It is exactly the same as logic, how these logics and or not are especially and or, not is special case, but and or is exactly as we implement them by hardwire. Instead of wiring the devices in series, we just connect the contacts in series in PLCs, or parallel connection, parallel connection, wiring connection of the devices, switches in the hardwire to implement OR logic. Similarly, in the PLC, OR logic is just a parallel connection of the contacts. Regarding the NOT is a special case. For the NOT, it's similar to the inverter. In the PLC is the same, but please notice that when we look at this contact, even a normally open contact, both of them, it consists of two variables, let's say. One of them is the variable that we see here, okay? And the other is the contact. The state of the variable, let me go to this, for example, here, this is equivalent to the buffer. So the state of the variable is the state of the input of the buffer, and the state of the contact is the state of the output of the buffer. For the buffer, they are the same because it's just a buffer. But the important part is for the NOT logic. The input is the input, the state of the variable, that the variable address that we see here is the state of the input of that, and the state of the contact is the state of the output. And please notice, it is the state of the contact that is important from when we look at this, whether the light is on or off. If the state of the contact is 0, then the light is 0. If the state of the contact is 1, then the light is 1. The state of the light is 1. And when the state of the light is 1, 24 volt is applied on the DC, on the output device, and then, for example, the pilot light turns on. So this is something that is important, and according to that, depend on the type of the switch outside of the PLC and the type of the contact inside of the PLC, the state of the output might be different. We will look at that in the example in more detail. Let me just skip that. We will work on that in detail. The other thing that we studied was a bit memory that we studied, that these bit memory that start with M, similarly byte number and bit number are used to store the internal variable. Okay, so just store some logic result somewhere and then use that somewhere else. Skip this part, and then we work on the how to convert an electric hardwire control system to PLC base. Instead of working on this example that we have already studied, we're going to work on this example, and you'll see that some of the details regarding the normally open, normally closed, and like that, we will work on that using this example. But before starting this, we reach to this part, and from now I'm going to work on this one. But before that, I want to ask you if you have any question regarding this part. This was just a review, fast review. If you have any question, please ask. Before that, let me mention that Jorge has already ordered some license key for all of you. Up to my knowledge, my communication with Jorge, he has not yet received the key, but it will be soon, maybe today, hopefully. And then it will be provided to you. And so then you can download simply the program, the main program from the Siemens. You can do that now. Open an account in the Siemens portal, in the Siemens site, and download the program. But for the license key, without the license key, you cannot use that. You can open that, but you cannot use that. But the license key will be provided soon, and then you can use that license key together with the PLC SIM. PLC SIM is also, you can download that and install. So you may do these two parts. And then when the license key is given to you, you can start programming. This is the news that I have not yet get any update from yesterday to know whether he has already received the license key or not. But as he will receive the license key, we will send that to you. Okay, so let's work on this example. We want to. This is the example of a heater system. This heating system is something that let me see. Okay, I have in the Amotral trainer, you have a heating system. Okay, and this program can somehow be used on this one, and the PLC program that I have provided as a PLC program is based on this Amotral. In fact, you have a heater. This is the temperature control system. You have a fan and a heater. The fan just turns on and off when this is enabled. The heater, you can turn it on and off. Let me increase the size of that a little bit. Okay, yeah. Here you see that you have a heater that there are some solid state relay for that, but to turn the heater on and off, to turn it on, it is connected to digital output 0. Digital output 0 means Q0.0. This is something that Amotral call that, but from the PLC, from the Siemens point of view, this in fact is Q0.0, digital output 0. If the digital output 0 is 1, then this solid state relay turns on and the heater turns on. If it is 0, it turns off. In addition to that, there's a temperature switch. This temperature switch, in normal state, it is closed. Please notice, in the diagrams, for all of the diagrams, the switches are indicated in their normal state. It means that when everything is normal. For example, in this case, this is a temperature switch. If the temperature is low, it's not high, so it is not hot, let's say. You see that the switch is closed. So the switch is closed. And so as a result, the one terminal of that is connected to 24 volt and the other is connected to digital input 3. Again, digital input 3 means input 0.3. In fact, from the PLC point of view, from the PLC Siemens point of view, it is input 0.3. Amotral, for simplicity, called that digital input 3. So it is connected to that. So if this digital input 3 has 24 volt, it means that the switch is in its normal state. So it means that the temperature is not high. It's not high. When the temperature is high, this switch opens. This is a temperature switch. This switch opens, and so the digital input DI3 voltage is 0 volt, and as a result, the input 0.3 becomes 0. Using this information, we can, because you see that this temperature switch is not connected to the heater. It is not connected to the heater. It is individually connected to the input, digital input. In our program, we use this state to turn on and off the heater if the temperature is high. Okay, this is the process that we are going to use. The program here is a hardwire control system for that. Of course, this hardwire control system is not implemented here. These are not connected to each other for the hardwire. But what's going to do is this. Here we can see that we have a start-stop and the heater relay. This is the heater relay, and this is the overheat or that temperature switch, overheat or temperature switch. You see that there's a, this shows that it is a normally closed type of switch because in normal state it is closed. When the temperature is high, it opens. Then you can see that, and also the stop is a normally closed switch. So it means that the voltage, this is not a PLC program, please note it, this is just a hardwire control circuit, these are wiring. So here, the voltage past its stop, and then if you push the start push button momentarily, this closes and then the heater turns on. And then the heater relay turns on, the auxiliary contact of that relay, is also closed. And so even when we release the start push button, this time the voltage reached to the heater through this path. So initially through this path and then through this one. Okay, and remain on until either we push the stop, so open the circuit at this point, so the heater turns off, and so the contact also, the auxiliary contact of that opens, and so the heater turns off, and even when we release the stop push button, it remains off, or if the heater, the temperature of the heater is high, so there's a overheat. And also just to indicate to the operator that the heater is on and off, there's a green and red light that depend on the state of the coil, or let's say the contact. Two other auxiliary contact of that is used. I add one more in this circuit. There's not any, but I add one more, let's say, wiring here, just to indicate that the overheat happens. So this green light is on when the heater is off. But why the heater turns off? Somebody pushed the stop, or it was the overheat. These are two different states. And maybe from the operator point of view, it is important to know that, okay, whether the temperature was high and as a result the heater turns off, or somebody pushed stop that. Pushing the stop is not a fault, but not an okay. That's fine. That's something maybe operator wants to stop that. But if there's overheat, it means that maybe there was something wrong in the process. So we need to know that. So if the same overheat is used here to turn on a yellow light, if the overheat here. So if overheat happens, so it means that when this becomes 0, oh yeah, that's correct. When this becomes, when this is 1, the yellow is off. Oh, if it is 1, it means that, oh yeah, if it is closed, if this is closed, this is open, and so the yellow light is off. When this opens, this closes. This is not of this, and so the yellow light turns on. So by looking at the yellow light, the operator can understand that, okay, there was an overheat. This is just a simple modification. Okay, but how to convert a hardwire control circuit to a PLC-based control circuit? It is very like driving. I mean that in driving, there are some rules. There are some books, there are some rules that do this, do that, but these are base. Then you should drive, you should sit and drive, and little by little get familiar with them and get and be experienced on that. So do experiment, do work with that, and little by little become quite handy on driving. Similarly, for converting hardwire control system to PLC based, and similarly for any PLC, any programming, it is the same as any other programming. There are some rules. We should start with those rules, but many of the important points we studied that during working with the system, during doing programming, during converting hardware control system to PLC-based control system, and get familiar with them. So these are just the base rules, but we should work on them. And then, okay, assume a hardware control circuit is given. The following steps. First, identify all input field devices, all output field devices, and all devices that could be programmed using internal relay. This is important. Here we have some contacts and switches, okay? And we need still a stop push button and a start push button. Even when we are going to have a PLC-based control system. Even in the PLC-based control system, still we need that start and stop push button. So these two switches are input devices to the PLC. These are devices that must be connected to the input module. For the heater, it gets command. So according to the logic, it gets the command from the PLC or from the control system to turn on or off. So this is an output devices. Similarly for the pilot lights, these are output devices. These are the devices that we send the command to them. So these are output devices. Similarly for the overheat, overheat is an input device. It must be connected to the input because it sends the temperature and send the information to the logic, to the control system. Send that information regarding whether there is overheat or not to the control system. So overheat sensor or overheat switch, temperature switch must also be connected to the input device. So it is very important to recognize which devices are input devices, and those devices are generally the sensors, the switches that send some information. This information doesn't mean some data or some, I don't know, page of data. No, just some information. That limit switch has energized. Somebody pushed that push button or something like this. Okay, that's the state of that. So these are input devices, and output devices are the devices that are energized according to the control logic, like the coil amp. There are some devices that in the hardware control circuit, that we need them just to implement the logic. They are not important by themselves. The heater is important by itself. The green and red light are important by themselves. They send some information, indicate something to the operators. But some of them, like these auxiliary contacts, are just used to implement the logic. Most probably, many of these type of devices that might be like this, just the auxiliary contact of them, or maybe some separate, some extra relays, contactors, and like that. We just use them because we want to implement some logic. Most probably, we don't need them anymore. All of them can be implemented by the internal memory in the PLC. We don't need them, but we should check. Please notice, let me warn you. Don't think that, okay, we never need them. I don't know. We should analyze that and look at that, but most probably we don't need them. So recognize that. Then select proper input and output devices and draw the wiring to connect them to the PLC. Okay, as I mentioned, wiring to the PLC is one by one individual. So for example, here, we want to convert this. So we, at the first step, we recognize that, okay, we need a stop push button, we need a start push button. Also, we need the sensors. All the sensors remain. We don't change the sensors. We cannot, let's say, remove the sensors. Sensors are sensing something in the field. So we need them yet, even when we have a PLC-based program. And then, depend on the type of them. I mean that, for example, normally open or normally close, okay? Draw the wiring and also connect them to the PLC inputs. Connect them to the PLC. Similarly for the output devices. Connect them to the output. But please notice there's not any connection between them. There's not any connection between them. There are some connection here in the hardwire between start and stop, but there's not any. Let me remind, this is not considered as a connection. This is just power supply. They are connected to power supply. There is not any logical connection between them. So all of them are connected individually. Then the next step, start with a draft PLC program that looks like the hardwire circuit. Okay, so if you want to convert the hardwire control circuit to PLC-based control circuit, the first step is just look at this and draw a PLC program here that looks like this. Maybe just very minor changes because of the formatting in the PLC, but it should look like this. This is not the final program. This is just a draft program, the initial program. We need to do some modifications. So let me start, draw that. I just draw that here. It's like this. Okay. In the PLC, we don't have these type of diagram symbols. In fact, this is a contact. So a contact that is connected to the stop. A contact that is connected to the start. A parallel contact that is connected to the edge, to the heater coil. Okay. Regarding them, okay, from the electrical point of view, there's not any difference with the heater is here, the overheat is here, or you can just switch the position of them. Even in the program, you can switch this part and this part. So instead of that, you may have this structure. It is the same. Stop, start, and edge. Okay, so there's not any difference. These are series connection to it. But regarding the edge here, edge, in fact, this is the heater. This is an output contact. In the PLC program, most of the PLCs, the output coil or the output assignment coil must be the one that is in the right side of the program. So not in between. So this is here. And generally, instead of course, both of them are depend on the PLC. It might be as a curve parenthesis or like as a circle. But this is the heater, and this is the sensor. So we just switch the position of them. And this is the overheat sensor. So you see that it comes from this, but maybe just a minor change because of the formatting. This is just because of the formatting of the PLC programming. It's just the shape of that, the order of them, but structurally it is the same. Structurally it is the same. And please notice, although this is normally closed, I do not put normally closed. I recommend do not that from the beginning. Everything normally open. And then in the next step, we should analyze them to see whether this should be normally open or normally closed. This is something that we will do that. So in the first step, this is. The second is this one. Okay, similarly, this one and this one. So this is for the green, this is for the red. This is H and this is H. Please notice I do not use the address format yet. We will look at the address format. These are just symbols, the tags or symbols, the start, overhead. But later we need to assign some number, input 0.1, 0.2 or something like that to each of them. This is something that we will do later. And for the overheat also, we can have this overheat. And then connect that to a yellow. Okay, so we need also a yellow here. Okay, so this is a draft PLC program. This shouldn't be here. I can remove this. Yeah, I can. Yeah, how to do that? Okay. Oh, I don't know. Yeah, this time. Okay. This is called a ladder program. It's the same as ladder diagram or ladder diagram program. It is the same as ladder circuit diagram. These are rails, and these called rung. We call them rung. Each of these are called rung. R-U-N-G, and these are in these two. Let's say so. Each of these parts. Okay, this is a rung number 1, rung number 2, or something like that. Let me just clean that. And these are rail. The left rail is in fact the power rail, the logic one. So all the times the logic of that is 1, or you can imagine as a voltage equal to 1 volt. Okay, just voltage as a voltage, 24 volt, 1 volt. But let's assume that this is the power supply for the logic 1, and here is the ground supply for the logic, or something like that. Okay, so if this is closed, the logic 1 reach to here. If this is closed, it reach to here, and if this is closed, reach to here, and then the heater turns on. Something like that, okay? But you can also imagine as a logic, not just as a circuit. Okay, so this is the next. This was the next step. Let's go to the. This is just a draft PLC. The type of the contact in the program depends on the type of the selected input switch and the expected result. Okay, here's something very important. This is a key point on deciding whether or not a contact in the PLC program must be normally open or normally closed. This is very important. Notice that from the operator point of view, both systems must work the same. So in fact, from the operator point of view, it has just a start and a stop. Operator don't care about or don't mind about, shouldn't mind about that, whether this is a PLC control system or it is a hardwire. Let's say it's as a black box. From the operator point of view, it is a black box. Operator see a start and stop push button, and operator knows there's an overheat, and in both of them. And both of them should exactly work the same. So, considering this in mind, we should analyze the circuit, this one, and also this one, and according to that, decide whether this should be normally open or normally closed. Whether this should be normally open or normally closed. How? Okay, let's start. For example, let's assume we are going to see to check whether this one is going, let me use another color, okay. Whether this should be normally open, this contact, this contact it should be normally open or normally closed. Okay, these two systems, this hardware control system and this PLC based control system must work exactly the same. Okay, so let's look at this. Let's assume that, okay, nobody pushed the stop, so it is closed. The temperature is not high, okay, so this is closed. And then what should happen if the operator push this push button, the start push button? In that case, this closes, and so closed, and this is also closed, so the heater turns on. Okay, this is something that we expect. So look at here. Let's assume that nobody pushed the stop push button. So it is in its normal position. We just ignore that. We assume that it is closed. Also, there's not any overheat. So we assume that it is closed. And just concentrate on the start. If these two are closed, and if you want to, something that we expect is that when we push this, we expect that the heater turns on. If the heater is going to turn on, we should have 24 volt at this point, or 220 volt, okay, depending on the supply. But just let me simplify everything to 24 volt. So we need 24 volt here. If you want to have 24 volt on the heater, when we push this, the logic of that should be 1. So the logic of this should be 1, okay. If I want to have the logic 1 at this point, when I push the start, look at this. When we push the start here, this is a normally open. When I push that, this becomes 24 volt. And so the logic of this becomes 1. So the logic of this is 1. So up to this point, I know that when I push the start, the logic of the start is 1. But on the other hand, I need this to be 1. If it is going to be 1, from the start point of view, from this start contact point of view, this must be 1. If this is 1, and this also, we assume that they are 1, okay, we are just concentrating on the start, so we assume that there's not any thing wrong with them. So the only thing that we need to turn on the heater is that this contact becomes 1. Then we push the start. Okay, so when we push the start, the logic of the variable is 1. Something that we need is the logic is 1. So they are the same. These are the same. It means that we need a buffer. So we need a buffer. So the type of this contact must be normally open. Let me remind again. Normally open, it works as a buffer. A normally closed works as an inverter. Okay, here they are going to be the same. So a buffer. That's good. That was not that difficult, but let's look at the stop push button this time. This time, let's assume that the heater is on. Okay, the heater is on, and then somebody pushed the stop push button. Something that we expect from the hardware control system is that if this is on, when we push the stop push button, this opens. Okay, when this opens, as a result, this turns off. Okay, this is something that the operator expects. Exactly the same must happen in the PLC-based control system. Okay, let's assume that the heater is on. So this is one. Then somebody pushed the stop. Push this. We expect that the heater turns off. Okay, if this heater is going to turn off, the voltage on that should be 0 volt. So the logic at this point should be 0. So the logic at this should be 0. Let me use another color. Okay, just another color. Okay, this color, for example. So this must be 0 volt. And so the state of the logic of the output image memory must be 0. And so this must be 0. Okay. When we push the stop push button, this opens. So how much is the voltage here? Can you let me know? When I push this, this opens. So how much is the voltage?
Zero.
Any suggestion?
Zero.
0. Perfect. Yeah. This becomes 0 volt. If this becomes 0 volt, the logic of that is 0. So the logic of the stop is 0. Okay. What caused the heater to turn off from this contact point of view? I want, it is 1, but I want it to become 0 when I push this. What is the state of the logical state of this contact that is required to turn the heater off?
Should be normally closed.
No, just don't think about normally closed or normally open. First, think about the logical state, whether it should be 0 or 1. I want to turn off this. I want to turn off this. If it is going to turn off, this must be 0. So what should be the state of this?
1.
Oh, okay. If the state of this is 1, why this should be become 0? This is very.
Okay,
this is,
ask again. Ask again so that we can answer you well.
Okay. You see, this is the trick on that. When we look at this, it is normally closed, but it's not necessarily be normally closed here. We should analyze that. Okay, let me repeat that analysis. Something that we need is this. When operator push this, what we expect is that the heater turns off. If the heater is going to turn off, the voltage here should be 0 volt. And so the logic should be 0. So the logic should be 0. So something that we need is that when we push the stop, this becomes 0. From the stop contact point of view, if we want to make it 0, this must become 0. If we make it 0, then this becomes 0. Because when it is 0, it means that this is open, and so the logic cannot reach to here. Or let's say this is a series connection. In a series connection, you know that it is a series connection. So it's like this, stop. It is connected to a and then we have this OR logic here. It is start. And H, okay, and here we have overheat, okay. We want the heater to be 0 by doing something here. This must become 0. So this must become 0. And please notice, something that we need is that the logical state of this contact to be 0. If this becomes 0, the heater turns off. On the other hand, when we push the stop push button, the logic of this variable becomes 0. Again, these are the same. These are the same. So again, we need a buffer. We need a buffer because the logic of the variable and the logic of the contacts are the same. Okay, let's look at this one. This one. Here, something that we expect is this. When the heater is off, we expect that the green light, so when the heater is off, the green light should be off. And if this is on, the green light should be on. This is something that we expect, or let's say the operators expect. Okay, look at here. This is the same variable. This is the same variable, the variable of this memory. So we use the same variable. So the state of this heater, this coil, is the same as the state of this variable. Something that we expect is that when this is on, okay, oh, sorry, I made a mistake. Oh, okay, sorry, I made a mistake. When this is off, okay, this is a normally closed. When the heater is off, this is closed, and so the green light is on. Sorry, this is on. And when the heater is on, the green light is off. In fact, the green light shows whether it is on or off. If the heater is on, the green light is, if the heater is off, the green light is on and the red light is off. When the heater is on, the green light turns off and the red light turns on. So the red light is opposite. This is off, and at this point it is on. Okay, here you see. Something that we expect is that when the heater is off, the green light to be on. Okay, if the green light is going to be on, this must be 24 volt. And so the logic here should be 1. So the logic at this point should be 1. On the other hand, when the heater is off, this is 0. And so this is 0. But if this is 0, this cannot be 1. If this is 0, the contact must be 1 if we want the green light to be 1. So when the heater is off, we want the green light to be on. So the logic here should be 1. And so the logic of this contact must be 1. But when the heater is off, the logic of H is 0. These are not the same. These are opposite. So we need an inverter. An inverter is a normally closed. So this must be normally closed. Okay? Similarly for this one, let's look at this one. When the heater is off, the red light should be off. And when the heater is on, the red light should be on. We can analyze just either of them. We can analyze this case or this case. Let's this time analyze when the heater is on. Okay, when the heater is on, we expect that the light to be on. Okay, if the red light is going to be on, here we should have 24 volt. If you're going to have 24 volt, the logic at this point should be 1. So the logic at this should be 1. On the other hand, when the heater is on, the logic of this coil is 1. If the logic of this coil is 1, the logic at this point is 1. And this is something that we need here, because if the red light is going to be on, the logic of this must be 1. And since these two are the same, so it should be normally open. So by analyzing the circuit, we can decide whether they are going to be normally open or normally closed. Let me emphasize that never look at these and say that, okay, this is normally closed, so this should be normally closed. This should normally open, so this should be normally open. Sometimes they are opposite. Like this one, it is normally closed, but this becomes normally open here. Because in fact, a combination of the state of the switch and the contact and the requirement is needed to be analyzed to decide whether this is going to be normally open or normally closed. Whether this is going to be normally open or normally closed. So we cannot just look at this and then according to that say that this should be normally closed. Although this is normally closed, this becomes normally closed, this is normally open, this becomes normally open. But you cannot say from the beginning. We should analyze that. Sometimes it is opposite, like this one. It is opposite. So it's very important to analyze that and keep in mind that this is important. Notice that from the operator point of view, both systems must be working. This was the reason that I mentioned here. It is a draft PLC program, just a draft. You start with a draft PLC program and then by analysis decide whether this should be normally open or normally closed, each of them. Normally open or, and even regarding whether we need an external, for example, some of the devices, we know that like these devices that we need sensors or switches outside of the PLC or coils and lights outside of the PLC. But so for some of the variables like this auxiliary contact, we should decide whether we need them or not. In this case, we don't need them. Why? Because it was very messy. Let me go to the next page that they have the program in clean shape. Okay, so this is the program, the whole program. Don't think about this green. I will tell you what's that, these green colors, but this is the program. You see that normally open, open. These are normally open. Regarding the auxiliary contact, this is also very important. Why we need these auxiliary contact? To keep the command. In fact, we push, this is a push button. A push button is a button that are connected momentarily. You just push that for a short time and release that. And there's some spring on that that release that. So this is closed just for a short time, momentarily, but we want to keep the command. So we need to do that. This is the way that we use that. We use the auxiliary contact of this. The state of this is exactly equal to the state of this. I mean that when this is energized, this is closed. When this is de-energized, this is open. Okay, so something that is important on this auxiliary contact is that its state is exactly equal to the state of the coil, of the contactor. Energized, de-energized, open, close, open. So when the coil is energized, the contact is closed, and when it is not energized, so this is open. So something that is important on this point is to have the same state of this.
Question, please.
Yeah, go ahead.
Is this the same concept we call latching?
Latch, yeah, this is exactly latching. Yeah, exactly, this is latching.
Okay.
Okay, but we have some latching assignment that we will study later in the next session. We have some special latching coil, but this is not a latching coil. This is a normal contactor. This is it's not a latching relay or latching contactor. This is a normal contactor, typical contactor, but we use this to latch. Exactly, to latch that. Exactly, that's that same concept. Exactly the concept that we're looking for.
Right.
Or seal in, it is also called seal in. Yeah, seal in or latch contact. Okay, that's very perfect.
All right.
So in the PLC program, we don't need to use any auxiliary contact of this contactor. We don't need, because we know this is something that we have already generated. So we know what is the state of that. So why we need to use another contact, for example, here for the auxiliary contact of H? We don't need this. We know what is the state of that because this is something that we have already generated. So we can simply address that here. You know that I mentioned that this is connected to, this is in fact, this is represented by a memory bit, a bit in the memory, in the output image memory. So it is something available to the program. So we don't need any external contact for that. We can simply use the state of that memory bit here. So the address of them are the same. So every time that this is 1, this is 1. Every time this is 0, this is 0. The same as the latching. So we don't need that. Okay. So this is how we convert a PLC-based, a hardware control system to a PLC-based. Although nowadays we don't, most of the times, I can say more than 90% or even 95% or even more percent of the time, we are not going to convert an electric control system to a PLC control system. But this conversion is very important from the concept point of view to understand some aspects on the PLC program. Something that we generally use is the process description that we will look at that in a few moments. But anyway, this is the program, and this is the program that based on, this is the symbolic, the program in symbolic. There's not just a start to stop, but not the address of the PLC. These are the symbols. But this is the program that using the PLC, using the PLC, Siemens PLC in the format of the PLC Siemens stop input number 01, start input number 00. Why 0100? I use that because of, let's go to this. Here, if you see the armature, it has 4 push buttons, a red, and 2 black. Generally, you use green for the start and red for the stop. And here you see that the green is connected to digital input 0 and red to the digital input 1. And you see that the green is normally open and the red is normally closed. So I assume that when you're going to work with the armature, you can use this as a stop push button and this as a start push button. Normally open, normally closed. This is connected to 0 and 1. So let's look at the program. Yeah. Stop is connected to input 1, 0.1, which is digital input 1, according to the armature, and input 0, digital input 0, 0.0. For the overheat, okay, let's again look at here. For the overheat, in fact, it is this sensor, temperature. Digital input 3, so input 0.3, and so the same. And for the digital out, for the output or for the heater itself is DO0, so Q0.0. So Q0.0 is used for the heater. So this is, in fact, if the Q0 is 1, the heater turns on in the trainer, and this is for that temperature switch. Also for the green, red, and yellow, 7, 5, 6. And here you can see, where is that? Here you have yellow, green, and light. Digital outputs 5, output 6, and output 7 are in fact connected to, these lights are connected to the digital output 5, 6, and 7. So if this is the logic of the Q0.5 is 1, this light turns on. If the logic of the Q0.6 is 1, this yellow light turns on, and similarly for the green light. So these variables are selected to be consistent with the trainer. So you can simply build this program in your trainer, on the trainer PLC, and then download that, and then simply use these switches to, where's that? Simply use these push buttons to turn on and off the heater. These push buttons to turn on and off the heater, and if the temperature of the process increases to high value, this temperature switch turns off, opens, let's say, this activates, so opens, and the heater turns off. Or you can turn it off by that, and also using these lights, according to the program, these lights turns on and off. So this is a simple program. In the recorded session, in the first part, recorded session of lecture number 2, this program, I built that, so you can go through the detail on that, on how to build this. This is something that you can go through that. But something that is important is that when you have HMI, okay, in this program, I assume that you're not going to use the HMI. You're not going to use this HMI touchscreen panel, okay? You're not going to use just the PLC and the switches. But when you use the touchscreen HMI, then you can even change this or simplify that. For example, you don't need any more the start and stop push button as a physical hardware push buttons, these type of push button, these push button. You don't need this push button. You can have some icons here and just push that icon here. You don't need that input-output switches. Similarly, for these lights, we don't need these lights when we have this touch screen. We can change the color of some device, some objects here that shows that, okay, the heater is on or off, or whether there's overheat happens or not. In that case, this is the program. You see that very simple program, just this one run. We don't need. In fact, this is the diagram for the HMI, a start-stop icon. Just this is a touch screen. So pushing the stop, the process is start and stop. And also the color here, the blue, I use the blue for when the heater is off, similar to the green, okay? The green light, I don't use green because the green was here, so I use blue to indicate that it is off. And when the heater is on, this becomes red. So instead of having two pilot lights to turn on and off, green and red, to indicate that the heater is on or off, just changing the color. And also for the overheat, we don't need this yellow to indicate that there's overheat. We can just have a symbol of the some symbol of the sensor, a typical sensor symbol here, okay? And then when the overheat happens, not only this switch opens, as you can see here, okay, as you can see here, but also you can change the color of this part of the sensor from gray to yellow, to orange. This is something that in the program you see. And the program, so in the program, there are some changes. Instead of, let me increase the size. Okay. We don't need input-output, okay? So from the hardwire point, from the wiring point of view, we don't need any hardwire input-output switches. They are here, and they are the information exchange through the network between the Profinet network between the PLC and HMI. So we don't need this hardwire, and we don't need any terminal, input terminal for the start and stop. But these are internal variables. These are the start and stop. At the previous one was output, was input signals. They need input modules. So the address of them should be I, input. But here, these are considered as internal variables. They come from the HMI. So we don't need input, they change to M10, M11. But the overheat, we need that. We cannot replace the overheat by the HMI. Because anyway, this should sense the temperature. So we need this physical temperature sensor. And also for the heater, we cannot replace the heater. We can change the color to indicate, so we don't need any more of the pilot lights, but we cannot replace the heater by HMI. HMI shows the state of that, but anyway, we need the heater to do the job. But the program becomes that simple. And also, it is very important that we don't need any hardwire switches. And this is very good, because when you don't need those hardwire switches, okay, we don't need to buy them, and also wiring. And also, the number of the input-output terminals that we use reduces. It means that we don't need too many input-output cards. Please notice that, as I mentioned, in small scale program, PLC program, we can use those compact PLC with some input outputs. But if we need more input output cards, or in a typical application, like in a pilot plants, or I don't know, something like that, refinery and like that, we need hundreds of input output cards. And they're expensive, and they need space. cabinet, electric cabinet, wiring, and this is a huge task, and a lot of cost of the control system is just because of these wiring and these input-output cards and like, or the switches like start to stop push buttons and like that, or pilot lights to indicate. All of them can be, or let's say a big portion of them can be indicate in the HMI. We don't need it anymore. And so the number of input-output cards reduces. The size of the cabinet, the amount of the wiring, wiring engineering, wiring installation and maintenance, all of them. And generally, although the HMI is expensive compared to one start to stop push button, but if the number of the input outputs is more than 10, 20, something like that, generally the price of the project reduces significantly. So you see that the program simplifies and also the wiring, but everything is here and it's more beautiful. It's very good, and you can later in some other examples we see that we can have some message here if there's some kind of error. In this one, it's just changing the color. Again, this one, how to build this part is also given in the recorded session. So I leave that to you to watch the recorded session, the second part for the lecture number 2. And let's continue for the process description. We are behind the schedule. If you have any question, please. Any question on this part? Okay. So the next part is how to build a PLC control system from process description. First, we look at what is the process description, and then look at how we can convert a process description to a PLC program. Okay, what is a sequential control, a sequence control? A sequence control, in fact, is something that we use to indicate the coordination between different actions, how they are coded. For example, let's assume that you have a machine, assembly machine. In this assembly machine, lots of tasks must be done, okay? And they should be in kind of order. For example, transfer the part, okay? Change the tool, okay? Feeding the metal cutting tool, okay? And then clamping and then drilling. You see that these are some steps that must be happen sequentially. We cannot change many of them, any of them, or maybe a few of them is changeable, but as a general, we cannot change. We cannot first do drilling and then transfer the part. It's meaningless. First, we should transfer the part, change the tool, use the proper tool, and then, for example, do the drilling or something like that. Okay, so there's a kind of sequence of tasks or sequence of actions. Let's look at an example here. Here we have a feeder with some material inside that, and 2 belt conveyor that the material transfer from the feeder to the belt conveyor number 1, and then from here to number 2, and then transfer to the next stage. Okay, let's assume that it is running. When it is running, it means that M2 is running, M1 is running, and the motor and this valve is open. It has a motor, a motorized valve, so the valve is open. Okay, and the material transfer to this conveyor, and then from here to here and there. Let's assume that you're just going to stop that. Okay, we want to stop that. We shouldn't stop all of them at the same time. For example, when the operator pushes the stop push button, if all of them stops, I mean that these 2 stops and this closes, it means that some material remaining on the belt conveyor. There are many reasons that it is not good. One of them is that some materials during the time start to react with the air, okay? So after sometimes maybe the properties of them change. The other one is that when we are going to start the motor, since it is heavy, generally the initial torque initial torque or the initial current that needed to start that is higher. You know that from the electric point of view, the motors at the beginning when they are stopped because of the inertia, when we start the motor, they need more current. And if there are material on the conveyor, because this is heavier, in that case we need higher current, and maybe the motor cannot, or there might be some damage on the motor, or maybe the lifetime of the motor reduces significantly. Maybe the motor was going to be work for, I don't know, 10 years, but after 1 year you see that the motor is gone. It's because of that high power, high current at the start. So something that we should do is that when the operator push the stop, first the motor should, this motor tree must close the valve. So first the valve should close. Then after some time, for example, 10 seconds, 5 seconds, depending on the length and the speed of this conveyor, or since this has a load cell and can weigh the weight of the belt conveyor, of the whole process, so by looking at the weight, the measuring weight, we can recognize whether there's material on that or not, or let's say there's significant material on that or not. If it is empty, there's no material, so the weight, it is light. So by measuring that, or by considering some duration, after this closes, then the motor of the conveyor number 1 stops. Then when the motor of the conveyor number 1 stops, then again motor of the conveyor number 2 stops after a while, either after some time or when the load cell number 2 recognize that there's not any material on the on the conveyor. And so although operator push the stop, but it takes maybe 1 minute, 2 minutes for this simple process to turn off the whole process. But the benefit of that is that there's not any material here, and when we turn on, since these are not heavy, the motor turns on. Okay, so you see that there's a kind of sequence on stopping, similarly sequence on starting, and for many systems, sequence on during the application, during the running of the system. So these sequences are important, and we should take care of them. A process description, in fact, is a document. It's a document, narrative document. It's just a text, okay? Mainly text, of course, not maybe some formulas, simple, or some figures, but it is mainly text. It's a text or narrative explanation of the process and the control requirement, like the sequence control. It is not a PLC program. It is not a logic diagram. It is not a control circuit wiring, hardwire control system. It's a kind of text that explains, first, briefly, at the beginning, generally, one paragraph. It depends on the process. If it is process, a small process, just a paragraph. If it is a whole process, a large scale process, maybe a few pages, 1 page, 2 pages, briefly explain the operation, what we expect from this system, what is this system, and then one by one, itemized, explain the detail or state the detail on each step on the process or the steps on the sequence control. And also, for example, here, this is just, this is not important for us, and I don't want to go through the detail on all of that, but just as an example, this is that's just a small part, of a process to convert the seawater to fresh water. Okay, so you see that at the beginning. Let me read that. Let's read them together. In the see, the first part is just explain the process. What is the process is going to do, and what are the main parts of that process? In the direct freezing method used to remove salt from seawater, the water itself acts as a refrigerant. In this process, there are essentially 4 steps: pressurizing, evaporating, freezing, separation, and discharging. You see that it's just an explanation of what is the process. and then one by one explain details on how it works. The process begins as the seawater enters a heat exchanger that cools the incoming water. Okay, this cooled seawater then enters the crystallizer, freezing tower, which is kept at a pressure of 3 to 4 millimeter mmHg, equivalent to about 0.005. Okay, atmosphere. Okay, this part is very important for us. This shows that, okay, so we need, there's not anything regarding control system, but this phrase shows that, okay, so we need a control system, a pressure control system. We need a pressure control system to keep the pressure at this level or this level of atmosphere. Okay, so it means that we should have a PID control or any other kind of maybe on-off control to keep that, and the rest. It's just a small portion of that. There's lots. Generally, for some process like power plants, thermal power plants, for example, the process description is in the order of the 500 to 1,000 pages or even more, or just the process description, because it's a larger scale plant. Of course, the refinery is much larger, but like power plant, that in the plants are considered as middle range, but anyway, it is quite large. It is hundreds of pages that explain different part, and for each part explains the control requirement. Any control requirement like this, that we need to keep the temperature in that level, or sequence of the action. Okay, these are given in the process description. The responsibility of us as control engineers is to read them. This is not prepared by the control engineers. This is prepared by the process engineers, the process experts, or the mechanical engineer, okay? But the control engineer, or somebody that is responsible to prepare the control logic, is to read that, understand the requirement, and according to that requirement, prepare the program, design the program. This is the responsibility. Sometimes the explanation is not clear. You are not going to generate or assume some consideration for that. We should ask the operators. We should return to the mechanical engineers. We should return to the process engineers and ask them, okay, what should be happen? For example, here, it just said that we need the control to be in this range. But, okay, do we have, what is the, let's say, the accuracy that they need, okay? And how much fluctuation is acceptable, or something like this, or which type of sensor is available. These are important. Whether we have to pressure switch to whether to measure that the pressure is less than 3 or more than 4, or we have an analog sensor that give us the pressure in any value. So these are something that we should check, and according to that, prepare the program. Okay, this is not a simple task, but it's really it's not simple task. But again, it is like driving. At the beginning, there are some rules to consider, but by doing the practice, by continuing writing the program based on process description, you become expert on that. Okay, let's look at a very simple example, and then a more practical example. Of course, this is also practical, but very simple. This is a process for drilling, okay, for drilling. Let's read the process description. It says that, okay, generally the process description includes some diagram also, some schematic diagram like this. This is from one, where's the reference? There's a reference, should be somewhere. This figure shows the sketch of a drilling process that requires the drilling press to turn on only if there is a part present and the operator has one hand on each of the start switches. And then This precaution will ensure that the operator's hands are not in the way of the drill. This is very important for the drilling and many systems like that, that it is possible by an accident, and this happens unfortunately sometimes in the workshops, that operator put the material under the drill, but and then push the start. And unfortunately, his or her hand is somewhere that hit by the drill. Okay, this is the same for the press, the high pressure pressing systems or like that. One practice is to have two switches that are not close to each other, so we cannot push them both with one hand. Intentionally, they separate them in the order of half a meter, not too much. Something around half a meter is generally sufficient. So operator needs both hands. It needs both hands to be on these two switches, and then both of them are pushed, then the drill works. If you push just one of them, it doesn't work. This is just for the safety. Okay, so here you see that it explains what that. And then, as I mentioned, this is very simple. Then it explains the control requirement. The sequence of operation requires that switch 1 and 2 and the part sensor, there's a sensor here. That sensor is just a kind of limit switch or a proximity switch or something like that. Then when the part is here, it sends that, or maybe optical switch. The sequence of the operation requires that switch 1 and 2 and the part sensor all be activated to make the drill motor operates. Okay, this in fact indicates the control requirement. Then it's explained that the program is after that. So this is something that we need. We have a drill, okay, a part sensor, a push button here, a push button here. So let's build a PLC program of that. We need two push buttons and so we have a 24 volt here. It is connected to push button number 1. Okay. And to the PLC card. This is PLC card, input card. Let me call that. Generally we use DI, digital input card. We have another push button that is connected to the PV2. And also we have a limit switch. Let me just indicate that as a switch, make it simple. Okay. That in fact is the part sensor. Okay. So these are connected to some inputs. Let's say input number, I don't know, 0.1, input 0.2, and input 0.3, for example. Okay, but we call them this. And we have a drill, a motor. So in the output side also, digital output, we have a drill, the coil of the motor. This is the coil of the motor. Let's call that, for example, Q, I don't know, 1.2, for example. Okay, this is the address for the output. And the PLC program is going to be this. Q12, or the motor, should turn on if the part switch sends the sensor, sends the part, and both of them are pushed. What should be the program? Can you help me? The program. It's a simple program. So I need a coil here for motor and the logic. What should be the logic here? To turn the motor on if the part sensor is activated and also both of them are pushed. So when this is closed and both of them are closed, what should be this program?
It should be a series connection.
Perfect. Perfect. Yeah, simple series connection. Very simple. It's very simple, but it shows that, okay, so PB1, PB2, and then part switch. Okay, that's all. So if either of them are not pushed, or if there's not any part here, the motor, drill motor doesn't work. So this is, you see that? This is the PLC program for this simple system. It's a very simple, but shows the general concept of that. This is the program and that. Okay, but what are the main steps? This was just as an example, but what are the main steps? Similarly, as I mentioned regarding the converting the hardware control system to a PLC control system, these steps or these rules are just the rules as the initial, let's say, a rule, but you should work with that and get familiar and become expert on that. So, steps to build a PLC program. Define the process to be controlled. Okay, that simple define that. What is the process? Draw a sketch of the process, including all sensors and actuators, and automatic and manual controls needed to carry out the control sequence. This is generally something that we have like PNID diagram or PFD or something like that. Generally, these are given in the PNID diagram if they have a process. List the sequence of operational steps in as much detail as possible. So here we just explain what is the process, but here those steps, as I mentioned, those steps, stepwise, one by one, what is the sequence, what is the control requirement. So this is just explaining. These are text. Up to this, and then draw the electric circuit connection of the devices to the PLC and determine the normal state of the switches. So we generally, as a control engineer, we are not going to select a switch to be normally open or normally closed. This is something that are selected by the process engineers or electrical engineers. I don't want to say that these are not going to be necessarily different peoples, but just as a task. Let's assume that we have a control engineer, we have an electrical engineer that take care of the electric circuits and motors and like that, and we have also a process and mechanical engineers. Generally, they do that parts. So they draw the electric circuit and they decide that. But anyway, this is something that we should at least check, to check whether the switch is normally open or normally closed. Is normally open or normally closed. Up to this point, in fact, it is not converting the process description to PLC program. In fact, up to this point is the preparing initial documents that the control engineer needs. That the process, description of the process, the diagrams, sensors, switches, the process description steps, and also the wiring. But generally, we should check them. And then by understanding them from here, we start to build a PLC. Build the PLC program requirement to actuate each output device. Consider different scenarios. Okay, we may build some program like the one that we did here, okay? Then we should consider different scenarios. What will happen if during working operator release one of the switches? What will happen? And that is something that is expected or not. So we should analyze that. So consider different scenarios. So we should check different scenarios where the process sequence may go astray and make adjustment as needed. And consider the safety. This is very important. Safety of operating personnel and make adjustment as needed. So at this point, we build a program initially, but then we should check different scenarios. And this is very, let me say, difficult, because in a small scale plant, that's fine, but in a larger scale plant, lots of scenarios might happen. And this is the responsibility of the control engineer to check that. And if, according to that scenario, something is expected or written on according to the sequence control or the process description, let's say, is not safe, we should report to the specialist that at this, according to this program, according to this process description, in that case, there's something unsafe happens. Or maybe they don't say anything regarding some parts. They didn't think about that scenario. We should let them know, okay, this also might happen. What should the control system do at this case? This is something that they should decide and let us know. And then we modify the program according to that. Okay, let's see an example. This is the automatic filling process. Okay, here you see a process description of that. A schematic diagram and some explanation. The first paragraph is just explain the whole general operation of the system, and then step by step some detail on the control system. Let's look at that in detail. The figure shows a sketch of a continuous filling operation. This process requires that the boxes, these boxes moving on a conveyor, be automatically positioned and filled. The sequence of operation for the continuous filling is like this. So here we have a hopper with the material inside. You have a belt conveyor or a conveyor, not belt conveyors, sorry, it's a conveyor. This conveyor runs by using a motor. So when the motor is on, the conveyor moves, runs, and so these boxes moving. It should be automatically filled, position and fill. So we have a photosense switch here to detect whether there's a box here or not, and we have a level switch to detect whether the box is filled or not. And we have a solenoid valve to turn on and off the valve in the discharge valve of the hopper. And we have a start to stop push button and some pilot lights. Okay, let's read that. Start the process when the start button is momentarily pressed. So we have a start and a stop push button that momentarily pushed by the operator to start and stop. But when it is start, then everything should be automatically works as it is expected. Stop the process when the stop button is momentarily pressed. So just a momentary push button. Energize the run status light, this run status light, when the process is operating. So when the operator pushes the start, this run pilot light turns on. Please notice this run pilot light doesn't show, according to this explanation, does not show that or does not indicate that the conveyor is running. It indicates that the whole process is on. At that every moment, maybe there's not any box here, the box is coming, or maybe the box is here and it is filling. So in all of these cases, the run is on. The energize the standby status light when the process is stopped. The whole process, not the belt conveyor, the whole process. Okay. Then stop the conveyor when the right edge of the box is first sensed by the photosensor. See, this is process description. It explains it just by narrative, but just by some statement, just as a text. It explains the control requirement. This box, or let's say this conveyor, of course, the conveyor must stop when this photocell sends a box. With the box in position, so when this sends the box, with the box in position and the conveyor is stopped, so after the conveyor is stopped, open the solenoid valve. So this must happen automatically. This is the sequence, you see, this shows the sequence. Open the solenoid valve and allow the box to fill. Filling should stop when the level sensor goes through, okay? So there's a level sensor that is off, let's say the voltage of that is 0. When the box is sufficiently filled with materials, any type of materials, this level sensor senses that. And so when this becomes true, this true should be in capital. It would indicate that this is the logical true. So when the logic of this is true, let's say the voltage is 24 volt, then the filling should stop. What does it mean? When the filling is going to stop, so it means that we should close the solenoid valve. So when the level is full, the solenoid valve should close. And then of course, the conveyor should work. Energize the full light. When the box is full, the full light should remain energized until the box is moved clear of the photostat. So when this is full, then this conveyor turns on and moves it to transfer the box. And this full remain on until the box is clear and of the photostat. So you see that this explains the process description. We should read that and according to that generate the program. Generate the program. Any question? Okay. The program, in fact, is given here, but it's almost here. It's 10:38. I think over there it is 5:38, and I don't want to continue. Keep you. I try to stop at 5:30. The lecture at 5:30, so you can go to your other task. But so we don't have any time to explain work on this today. We will look at this next tomorrow. Let's say tomorrow at the beginning. And but let me emphasize again that this is a program to implement that, and also this is the HMI. That tomorrow I will explain this HMI. This at the beginning we look at this program and also look at the HMI, the detail on the HMI tomorrow morning. Any question? Okay, any question?
It's not a question.
Yeah.
It's just a compliment and an observation that here in Kenya, Western region, the rain has been disturbing us. That's why you've been seeing us on and off.
Sorry, can you repeat and a little bit louder?
Oh, slowly. Okay, I just want to say thank you. It's a compliment for the lesson. Then just want to say it has been a challenge today, the on-off because of network and rains. When it rains here, there's no power. But we have still followed.
Okay.
Yes.
I record this.
Yes.
I download this and upload that again. Upload this
Yes.
session also in the model.
Yes. Yeah.
So if this happens, if the quality of the network is not good, or sometimes hopefully you can download that later. Okay.
Yes.
Okay.
Thank you.
Welcome. Any question? Any other question?
Excuse, I have another one. I have a question.
Yeah, go ahead.
This one goes to our friends in Kisumu.
Yeah.
I was just thinking, I talked with the administration. If they can facilitate us, we can come to Kisumu. We do some of the practicals there while we wait for the license key and all that. So I don't know if it's possible from them. Maybe they can just assure us.
It is possible. Hello.
Yes, hello, sir.
Yeah, it is actually possible.
Yes.
I'll confirm with my HOD.
Yes.
So that possibly tomorrow I'll let you know whatever he has told me.
Okay.
So the HOD will liaise with the management or the principal so that we can get the directive from them.
Yeah.
Yeah, actually that.
Okay, I'll be so thankful.
Okay, thank you. Well done.
And let me emphasize that all the programs are also uploaded. So for each, of course, those that are, for example, the automatic filling process, the program for this one, not for these simple examples, quick examples, but for the main examples, these the program, the PLC and the HMI is uploaded in as a file in the Moodle. You can download them, and when you have the access to the TIA Siemens software, you can also open that and look at the detail. And tomorrow, in fact, I'll show the detail of this program as an example. Yeah. Any other question? Any other comment?
Maybe a question.
Yeah.
When are we supposed to start on those practical exercises?
I assume that my expectation is that something that's expect that we study the, let's say, the theory or the base on the lecture in the asynchronous. Then in the recorded lecture that is associated with this synchronous, this is the activity, in fact, that I expect that you do. But I do that for you once the total steps. So watch that recorded session to understand what are the steps for the activity. And my expectation is that you do exactly the same. So when you have, if you have access to the, of course, those recorded sessions are based, I assume that you have the trainer. You have the trainer. The trainer that I'm using is different from the mechanical point of view, let's say from the structure, but it has the same PLC and the same HMI. It has the same. So the program is the same. And I also use the same input outputs as you have in the amateur trainer. So the same program you can use. So watch that and then follow that exactly. Follow that. In fact, it's a kind of, let's say, lab instruction, but instead of writing the instruction, it's recording. So follow that, build the program, build the HMI, download that on the PLC and test that. All of these are explained in the recorded session. But if you don't have the trainer available for our friend in the Sigalagala, or if you want to do more practice on any other time that you may not have access to the trainer, you can also use the PLCC. But the program is slightly different that I will let you know tomorrow. That the program should be slightly different from the programs that I provided, but the general steps are the same. So my expectation is that for each lecture, there's a lab experiment, that the lab experiment is given to you not as a instruction, but as a recorded session. It is more informative, and I expect, especially that I'm not over there. If I was there, it would be very simple, especially for me, to just prepare lab instruction. And when you were working there on the lab, I was there and help you any times that it is needed. But since it is a kind of remote, so we prepare a recorded lab instruction, let's say. So please watch that and do the same. Prepare the program according to that for PLC and HMI. Okay?
Okay.
Yeah. And then when you prepare the program, submit that according to the instruction that is given in the model. submit that, send that to me so I can check that.
All right.
Okay. Good. I just know that because from the beginning we expect that all of you has access to the trainer, but last week we understood that it's difficult for some of our friends to have access. So this is something that Jorge, I know that Jorge has already bought that switches, that license keys. It's just a matter of when he received those. As he received, we will send them. But he has already bought for all of you. So there's a kind of delay, but hopefully we can catch up. Okay, good. So see you tomorrow at 4 o'clock.
Okay. Have a good day as we are going to sleep.
Yeah. Okay. Goodbye.